name is Guillermo Balboa. I'm a PhD student at K-State Department of Agronomy, and today we are at the ASA, CSSA, and SSS Science Society meeting, and we are presenting a poster about some part of my PhD research. The title is Modeling a Corn-Soybean Rotation with APSIM in a Western US Corn Belt. The main idea of this work that we did here is to put together the information from 2 years data, 2014 and 15, from one experiment and one rotation that we have. It's a long-term study in corn and soybeans that we have in Scandia, Kansas. Basically, we have different treatments there, and the idea is try to understand which are the best management practices to close yield gaps. Okay, so basically we have 5 treatments there, going from what we call the common practices to what we call ecological intensification. Right. For this purpose of this poster, we just took 2 of the treatments that you can see here, what we call common practices and ecological intensifications. Basically, what we are doing is varying seeds, row spacing, fertilizers, micronutrients, fungicides, and insecticides across the cycle. So we have 2 treatments in corn and soybean, as you are seeing here, 2014 and 15. We have an irrigated study, but also we have a dryland phase. So this is a side-by-side experiment, and we switch the plots in 2015 to follow the rotation. During the growing season, we track biomass. We did biomass samplings, we did nutrient concentration in the tissues in these several growing stages in corn and soybeans, and then we put all that information in different runnings in APSIM model. So APSIM is a really friendly model that can help us to simulate what we are seeing in the field. So for the statistic, we use the relative root mean squares and the efficiency of the model to test this. Just to have an idea of what happened in these 2 growing seasons, we can see some pictures of B10 growing stage. This is what we call common practices, and this is what we call ecological intensification. And the number that you are seeing there is the canopy coverage, okay, that we analyze with the software. If we're moving to soybeans, we can see that there is a huge difference. And in soybeans, these pictures were took at before stage. We are going from 42% of coverage to 66% of coverage, and we will see soon in the yields that we have a huge impact in yields. Before going to the results of the simulations, we are showing here the corn yields and the soybean yields for both years. We pull all the data together. In corn yield, we explored that we don't have a big yield gap, because one of the explanations of this is that the fertility of the site that we were using and the methodological conditions for the growing seasons were good. But if we move to soybeans, and we can see maybe some residual effect of the nutrients that the corn could not use in the soybean. We saw huge difference in dryland and irrigated, going from 2.1 to almost 4 tons per hectare. And if we move to the irrigated side, it's a big difference in yields from 3.5 to 5.5. So we have 2 tons of difference in yield in that case. So having this in mind, we moved to, these are some pictures that we took at different growing stages. As you can see here, the common practices, the biomass that we can see with this reference here, is the plants are looking smaller, and we can see the inter-row spaces, but in this case the plants are looking bigger and we cannot see the rows. This is 15-inch spacing on your right, and this is 30-inch row spacing on your left. Going directly to the result of the simulations that we did, we took a special emphasis in the yields, biomass, and nutrient uptake for corn and for soybeans. Okay, and we evaluate, as I mentioned before, with different statisticals, which is the accuracy of the model to predict these traits. Okay, and we are seeing that for yield and biomass, we have a relative really good R-squared, 0.81, 0.79, 0.87, and for plant biomass also the R-squared is good, and the efficiency of the model is about 0.6 in average. We need to think that the efficiency is a number that can be negative, can be positive. If it is positive, it means that it's good, and if it is close to 1, will be the best. Okay, and we have values here: 0.59, 0.9, 0.51, 0.7 for yield and plant biomass for corn, soy, and soybean rotation. We saw that also the model is not doing that well for stem biomass and leaf biomass, but we are trying to see with all the information that we took if we can improve the model efficiency for the future, taking into account some physiological factors that we can that we measure and we might need to modify in the structure of the model. Okay. So the conclusion of this, in the case of going to the uptake, also has a relatively good explanation, but it's not as good the prediction as was with yields and plant biomass. So mainly the idea, again, to close this video is to show here one of the important tools that we can use to summarize all our information when we are doing research, as is the modeling. The modeling is a really important tool that can help us to summarize information and then to see if what we measure in the field can be simulated to then take this to real situations and try to understand, to have a better understanding of how the farmers can use different management techniques to close the yield gap.